Reading quiz 15 brings us to a different type of derivative. Remember, we've studied derivatives for polynomials and rationals and trigonometric functions. Hey, what's left? Exponential and log functions, right? So I'll show you how some of these formulas that we use for exponential and log derivatives are derived. But in the long run, it's probably best that you get your flashcards ready and that you write down the common derivatives that we will use throughout the rest of this course. So first of all, the basic exponential derivative formulas. The proofs are going to be left for class for most of these, although I will explain something with this. Derivatives to know for the exponentials are as follows. The derivative of a to the x, where a is a base that's bigger than 1, is a to the x times natural log of a. And the derivative of e to the x is just e to the x. I kind of said that without any excitement, but it really is one of the most extraordinary derivatives in calculus. What this particular formula tells us is the derivative of e to the x is itself, and it is the function whose derivative is itself. And that'll be a very useful thing that we will address when we get to differential equations and we talk about rates of growth and that sort of thing. How does this formula come about? Well, if we're to just look at the first formula and take that on faith for the time being, the derivative of a to the x is equal to a to the x times natural log of a. Notice that if you plug in e as our base, we would get the derivative of e to the x is e to the x natural log of e. And we remember from our pre-calculus days that the natural log of e is just equal to 1. So this second part of the formula, the natural log part, reduces down to just 1. It's an incredible formula, and we will be referencing it at various points this year. If we include the chain rule, for example, if we had the derivative of a to the u, where u was some sort of a function of x, then the formula is the same, but we do need to make sure that we take the derivative of u with respect to x, as if it were an inside function, which it is. Same thing with e to the u. If we were finding the derivative of e to the u, where u was a function of x, we would get e to the u du dx. Some example problems. Suppose you wanted to find the derivative of e to the 5x. So I just said just a minute ago, the most wonderful formula, I think, of all of our derivatives is the derivative of e to the x is e to the x. The problem is we've got an e to the 5x. And what in the world do you do with that 5x part? Well, the 5x is an inside function. In fact, a lot of books will write e to the 5x as exp parentheses 5x to indicate that it is an inside function. And so we need to take the derivative of that inside function just like we would with any other chain rule problem. So our answer will be e to the 5x times 5, which is the derivative of the 5x part. And notice again that the natural log of e is equal to 1. In fact, that formula derivative of e to the x is equal to e to the x is just something that is derived from that a to the x derivative formula. And really that first formula is the one that you need to memorize, although the derivative of e to the x comes up so often you can't help it. Another example, derivative of 3 to the negative x squared, and also involves chain rule. And we find this derivative by taking the derivative of the outside function, which is 3 to the something, in this case 3 to the negative x squared, times the natural log of 3, natural log of the base, times the derivative of the inside function, which is negative x squared. Again, it's sometimes hard to see that negative x squared is the inside function, but that is what we are raising our base to. So the derivative of negative x squared would be that negative 2x part. Final example involving exponentials involves mixing in a couple of rules. So let's say we wanted to find the derivative of tangent of 5 to the x over x cubed plus x. The overriding problem here is that we have one function divided by another function. Well, what is the procedure for finding the derivative of a quotient? Oh, it's the quotient rule. Okay, so we will need to use the quotient rule on this problem, and be careful. We need to find the two derivatives separately. First of all, the derivative of tangent of 5 to the x will be secant squared of 5 to the x, the first outside function, times 5 to the x natural log of 5. That's the derivative of the 5 to the x part. The derivative of the bottom we've known for a while. We want to find the derivative of x cubed plus x, which is just 3x squared plus 1. Again, quotient rule says low d high minus high d low over low squared. Low is x cubed plus x. D high is that secant squared of 5 to the x times 5 to the x natural log of 5. That seemingly complicated statement. Minus high, tangent of 5 to the x. D low, 3x squared plus 1. Over low squared, x cubed plus x squared. Now, the log derivative formulas you need to know. Again, there's a general formula, and then there is the formula that involves our natural base e. The first formula is finding the derivative of log base a of the absolute value of x. And that formula, which we'll talk about in class, is just 1 over x natural log of a. If our base is e, as it is with the natural log function, then that natural log of e, again, becomes 1. And so our formula is that the derivative of natural log of absolute value of x is equal to 1 over x. Another pretty remarkable formula, which we'll cover a little later on in the course. Again, if we want to use chain rule, we have derivative of log base a of the absolute value of u is 1 over u natural log of a times du dx, because we have an inside function. So again, the derivative of natural log of absolute value of u with respect to x is 1 over u times du dx. So just like we did with the exponentials, you need to take the derivative of the inside function if u is a function of x. It's also important to note that absolute value in the natural log. The reason for this is that the derivatives of both of the following functions is the same due to the chain rule. So let's say you just want to take the derivative of natural log of x. Well, we just saw just above that that derivative is 1 over x. But if we wanted to find the derivative of natural log of negative x, we would get 1 over negative x times negative 1. Where does that negative 1 come from? It is the derivative of the inside function, negative x. And notice that the two negatives cancel out. And they cancel out to give you just 1 over x. So why not save ourselves some time? Remember, if we had x is bigger than 0, we could use natural log of x. And if x is less than 0, we can use negative x. The negative x will make anything that's negative into a positive. We then can combine this into one big statement by using the absolute value, and it makes our lives a whole lot easier. So here's an example. Let's say we want to find the derivative of natural log of absolute value of secant of x. That derivative would be 1 over the inside function, which is secant of x, times the derivative of the inside function, which is secant of x, tangent of x. The secant of x's will cancel out, and we're just left with tangent of x. Remember me, this is a formula we will see in a little bit when we go back to find antiderivatives. And it's important to see the derivative of this seemingly complicated statement, natural log of absolute value of secant of x, is just tangent of x. Another example. Let's say we want to find the derivative of log base 11 of e to the x. Again, the formula is 1 over the inside function, which is e to the x, times the natural log of the base. So in the case of a logarithm, the natural log will go in the denominator. In the case of an exponential, that natural log stayed in the numerator. Don't forget we need to use the chain rule, take the derivative of the inside function, which is this e to the x. Hey, the e to the x's cancel out, and we're just left with 1 over natural log of 11. The reason for this seemingly strange statement is because if you remember, logs and exponentials are inverses of each other, and so you do get this constant 1 over natural log of 11. A final thing I'd like to talk about is log differentiation. Logarithmic differentiation is a technique that we'll employ, which will have us take the log of both sides and use our new log rules. So when we have a situation where both the base and the exponent have a variable, we want to try this particular technique. And what this technique will do is have us take the logarithm of both sides and use the properties of derivatives of logarithms to find the derivative of the original. So here's an example. What am I talking about here? Y is equal to x to the x. Notice that the base and the exponent both have an x involved in it. Now you can use log differentiation in other circumstances, but it's most useful in these particular circumstances. We're going to take the logarithm of both sides. In doing so, we get natural log of y is equal to natural log of x to the x. Well, one of the properties of logarithms, one of our log laws, is that we can take an exponent inside of a logarithm and move it out front as a coefficient. In doing so, we get natural log of y equals x times natural log of x. Now we can go ahead and take the derivatives. This will usually involve some sort of a product rule or implicit functions. So derivative of natural log of y would be, with respect to x, would be 1 over y times dy dx. All right? That's, remember what we did when we did implicit functions. Derivative of x times natural log of x will involve the product rule because it's x times another function, natural log of x. All right, that derivative would be x times the derivative of natural log of x, which would be x times 1 over x, or 1. And then natural log of x times the derivative of x, which would be natural log of x. We can move the y over to the other side and get dy dx is equal to y times the natural log of x plus 1. And remember, y was equal to x to the x. So we get this formula that dy dx is equal to x to the x times natural log of x plus 1. Now, you would think you would either maybe be able to use the power rule or be able to use the exponent rule for this particular situation. But in fact, what we have to do is some strange mix of the two. You'll notice that if we were to distribute this statement, we would get x to the x times natural log of x plus x to the x, which is some sort of a combination of the two. All right, the x to the x times natural log of x would be as if we were to use the exponent rules. And the x to the x kind of has a little bit to do if we were to use the power rule.